Absolute value functions day 1. This comes right after piecewise functions. Hopefully you remember from math classes in the past that the absolute value of a number x, which is written with vertical bars on either side of it, is the distance that number is from 0 on a number line. Notice that the absolute value of a number is always non-negative. So it's positive unless it's 0, and then of course, if it's 0, it's 0. Now the reason why we do absolute value right after piecewise is because an absolute value function can be written as a piecewise function. So we have the absolute value function equals x when x is greater than or equal to 0, and it equals the opposite of x when x is less than 0. Okay, so for instance, if our absolute value, we're trying to do 4 when it's greater than 0, but if we put a negative 4 in, it still becomes 4, so we take the opposite of it. So we put a negative 4 in here, it's less than 0, that means we would take the opposite of negative 4, and it would still be 4. Okay, so we can write that as a piecewise function. Now, today we want to see what the shape of a absolute value graph is going to be. So let's take that piecewise function that we were just talking about and graph it. So if we put 0 into the absolute value function, we know we're going to get 0 back out. So 0, 0 would be our first point. Let's do some more positive points. If we put 1 in, we get 1 out. 2 in, 2 out. So we have this pattern on the right side of dots, putting numbers in, getting that same value back out. Now on the other side, if we put a negative 1 in, that's less than 0, but we would need the opposite of it. So negative 1 would be 1. Negative 2, the opposite would be 2. So when we go to graph it, that's on the left side of the y-axis, but it still is we're going to the left, of the y-axis, I said that right. So our x values are negative, but our y values are still positive. So you will see that we are making a V shape because we want all of our y values to be positive regardless of what we're substituting in for x. So all absolute value functions make this V shape. So anytime you see a V, you'll know it's absolute value. The graph of this piecewise function consists of 2 rays which meet at a vertex. That 0, 0 right there is our vertex. It will always be V-shaped, and it currently opens up. We may change that a little bit in the future, but right now it's opening up. Domain, our x values. Well, we can continue putting numbers in forever to the right, forever to the left. So forever in math tells us that we could go to infinity. Now, interval notation we talked about the other day. And you'll notice that I am writing this infinity for the domains with parentheses around it. We talked about how parentheses means not included. The reason why infinity is not included is because we can't ever actually get there. So the only time we use a bracket is if it's an actual number that we can get to. Infinity is not something that we can actually get to. Now range, on the other hand, is our y values. Let's look at our graph. Our y values, we don't have any down here at all. The first y value we have is 0, and then it continues up from there. So on our range, we will have a bracket for 0, because 0 is included, and it will go to infinity, but we can't actually reach infinity, so it'll be a parenthesis. All right, so next up is a graphing calculator exploration. So if you have that, grab it. And this will be one where you'll want to pause frequently to try these in your graphing calculators because it takes a while to find the buttons that you need to find. So first, the other day we went to your y equals and we put your greatest integer function in there. We're going to go the same place to graph your absolute value. So you will go to y equals, and if there's something in there, clear it out. Remember, we went to math, the math button, and we went over to number. So before we picked int when we did the greatest integer function, but today we're picking this very first option, ABS. That's absolute value. So you're going to hit that. Some calculators will have these vertical bars. Some of them will just say ABS. It doesn't matter. Either way is the same. So you'll put an X in there and then get out to graph that absolute value. Then hit graph, and you'll see the V shape if your window is in the standard form. Remember, if it's not, you can hit zoom 6 to get a standard window. So we're going to sketch that here. Here's our parent function is what we call this one, because everything else is going to be based off of this one. So I want you to take a minute and go through the rest of these. So hit pause on the video and go and graph in your Y2, so that's the next one down. When you go back to your graph, you're going to go to your Y2, and you're going to graph 2 absolute value. In your Y3, you'll put 3 absolute value. So I'll show you, for instance, you'll go to 2 absolute value X, and then go down to Y3 and do 3 absolute value X. So for that first exploration, you'll have, your screen should look like that, where your Y1 is the original absolute value, your Y2 is 2 absolute value of X, and your Y3 is 3 absolute value of X. Then you'll graph it and sketch it. So you have several of those that you need to do all the way down the page. So hit pause, do all those, sketch them, and then come back and see if you have the same sketches that I do. Okay, so now that you have done that and you are back, hopefully for this one, what you noticed is that you had your parent function that we originally graphed, just like up on number 1, but then the graph of 2 and 3 looks more like this. So what happens is it got narrower, and we call that a vertical stretch. Now, when we say a vertical stretch, we also will give the value by how much it's stretched. So for the first one, we'd say a vertical stretch of 2. The second one, we would say a vertical stretch of 3, if we were describing the transformation. All right, then the next one, hopefully you left your parent function in Y1, because it needs to be in there for all of these to be able to compare. So our blue one here is the parent function. And then the next two, with coefficients less than 1, got wider. We call that a vertical shrink. Okay, so that's what happens when your A value, that's the value that is out here, is less than 1. Whereas vertical stretch happens when A is greater than 1. Now you might be thinking to yourself, well, what happens when A is 1? Well, think about that. What happens when you multiply something times 1? Nothing. Okay, so it just keeps it the same. So there's not a stretch or a shrink. All right, on number 4, we have our parent function. We threw a 2 coefficient in and then a negative 2. So we already talked about what the 2 itself does. That's a vertical stretch, makes it narrower. But what would the negative 2 do? Well, hopefully you saw that it was an upside down V. So what we would say is that is a reflection over the x-axis, and we had a vertical stretch of 2. Because our A value is greater than 1, so that tells us our vertical stretch part. 2 tells us by how much, and then reflected over the x-axis. So anytime there's a negative out here, it will always be a reflection over the x-axis. Do make sure you're using this terminology. This is very specific terminology, but is one that you need to make sure you're using. Don't use any other words to describe it. All right, number 5. So we have our parent function. Always use that to compare all of these. And then we had one that had an absolute value plus 2 on the outside. You should have seen that it moved your absolute value function up 2. And then the next one moved it down 3. So we would describe this first one as a translation up 2, and then the next one would be a translation down 3. The last one, we have the adding and subtracting inside the parentheses, and it does make a big difference if it's outside or inside. So we have our parent function. When it said plus 2, you may have guessed that was going to go to the right 2, but it's actually the opposite. Plus 2 moves us to the left 2. And then negative 3 actually moves us to the right 3. And we'll talk more about why that is in a second. So again, those are translations also. We had a translation left 2, and we had a translation right 3. All of these transformations we should be able to figure out by just looking at the equation, because there is a rule that keeps it consistent for all absolute values. So we don't always have to use our graphing calculator. Here's the rule. So our A value, we found out, tells us the vertical stretch and shrink. But it also tells us something else. Remember, if it is negative, it's going to be a reflection over the x-axis. And we might make a note to ourselves on the vertical stretch shrink that it's a stretch when A is greater than 1, a shrink when A is less than 1. The H value moves us left and right. Now remember how it was opposite from what we thought? When it was a plus, it moved left, and a minus, it moved right. That's because there's a negative in the equation. So this H itself right here is actually a positive H. So this subtraction sign belongs to the equation. So this H is moving us right. When it's a plus H, that's technically minus negative H. So that's why it's moving us to the left, because it's actually a negative H. And then our K is going to be our translation that moves us up and down. And it's just like it, since it's a plus K, if it's positive up, negative down. Positive, negative. Now our vertex is always going to be located at HK. Remember to take the opposite of what you're thinking H is to find that x coordinate of your vertex, and then K is what it seems. We also always will have an axis of symmetry. That's a line that goes right down the middle of your graph that divides it into 2 equal pieces. So now that we know those rules, we can actually take a graph, or an equation I should say, and graph it without using our graphing calculator. So we're going to start by stating the vertex. Remember, the vertex is HK. So our H value, this looks like a positive 3, but really it's a secret negative 3, because remember, minus negative 3. So our H value is negative 3. Our K value is negative 4. It says describe the transformations. So we have this negative here on the outside. So that first one's going to be a reflection over the x-axis. And then our vertex helps us with the other transformations. We know that it's going to go down 3, and we know that it's going to go, left 3. That's what I get for writing and talking at the same time. Our H tells us left and right. left 3, and it's going to go down 4. All right, so now let's graph it. We know that our vertex is -3, -4. 1, 2, 3, 1, 2, 3, 4. I want to make sure we have our scales on here. Know what we're counting by. We know it's going to open down because there was a reflection over the x-axis. And we didn't have any vertical stretches or shrinks, so that means our slope is going to stay the same. It's still just going to be down 1 over 1 in each direction. So just like the parent function, we have this V shape that's opening down. Again, I will remind you, just hit pause if you need to catch up. Lastly, what we need to do is to state the domain and range. So our domain keeps going forever to the left, forever to the right. That's -infinity to +infinity. And then our range starts down here, and then it tops out right at that point right there. So down here, it's going to keep going forever, so that would be a -infinity. And then our highest point that it ever reaches on our y-axis would be the same thing as our k value of the vertex, so -4. We'll put a bracket with it. Now the other important piece of information that we talked about briefly up above was the axis of symmetry. The axis of symmetry is this imaginary line that goes right down the middle of your absolute value function, same on either side. And the equation for it is always x equals h. So in this case, our axis of symmetry would be x equals -3. So this vertical line here goes through the x-axis at -3. All right, we have one more graph to go. I want you to take a look at it, try it, see if you can do everything that we just did here. And then after you get all of that information, come back and check and see if you got it all correct. So hit pause, try it, and then come back. All right, hopefully you came up with 2, 1 for your vertex. An axis of symmetry would be x equals 2, because it's always x equals the x coordinate of your vertex. Then we need some transformations. This 3 out here tells me, because it's greater than 1, that I'm going to have a vertical stretch of 3. It's positive, so I know that I'm going to open up. Because of my vertex, I know that this is going to move right 2 and down, not down, up 1. All right, so if I put all that together, my vertex is at 2, 1. A vertical stretch of 3 affects my slope, so that means I'm going to go up 3 before I go over 1. Normally, a parent function just goes up 1 over 1, but a vertical stretch of 3, we're stretching that slope out. That's our vertical stretch. Connect the points to get our pretty little V. And then we want to state our domain and range. Domain continues forever to the left and right, so we have -infinity to infinity with parentheses. Range is our y values. Starts at 1 on our y-axis with a bracket, and then continues on to infinity. Hopefully you got that all correct. If so, well done. We'll do lots more absolute value graphing, so those transformations are really important to know and to understand.